Okay, ever just stop and think about what everything around you is actually made of? I mean, the chair you're sitting on, the air you're breathing, even you, it's all part of this incredible, invisible, constant dance. So let's jump right in and explore this amazing world of matter.
All right. To get us started, we're going to tackle a simple everyday mystery. It's one of those things you've probably experienced 1,000 times, but maybe never really stopped to question why it happens. Seriously, think about it for a second. When someone's grilling burgers or making popcorn, you can smell that deliciousness from super far away, right? But what about, say, a cold sandwich? You pretty much have to have it right under your nose to smell it. So, what's the deal? Well, the answer, it's hidden in the very nature of matter. Okay, so to crack this mystery wide open, we have to start with the basics. We need to figure out what matter is. And it all boils down to these tiny fundamental building blocks of, well, everything, particles. So the official definition is actually pretty simple. If something takes up space and has mass, boom, it's matter. And that's everything, from a massive star way out in a distant galaxy all the way down to a tiny little grain of sand. Now, for ages, scientists actually argued about this. Is something like a glass of water a solid, continuous thing, kind of like a pane of glass? Or is it more like a giant ball pit filled with zillions of tiny individual bits? Well, guess what? There's a super simple experiment that settles this debate once and for all. You can even picture this in your head right now. Let's say you take a glass of water and you mark the water level with a pen. Then you dump in a spoonful of salt and stir it all up until it completely dissolves. The salts, it looks like it just vanished. But here's the crazy part. The water level hasn't changed at all. So where did the salt go? And this is where we get our answer. The salts didn't just disappear. Nope. Its tiny little particles actually just slipped into the empty spaces between the water particles. This is our first major clue, folks. Matter isn't some solid, unbroken block. It's made of particles, and there are gaps between them. All right, so checkpoint. We've figured out that everything is made of particles, and there are spaces between them. Cool. But how do these particles act? What are they doing? Figuring that out is going to get us so much closer to solving our hot food mystery. Well, it really comes down to three simple rules that these particles live by. We already nailed the first one. They have spaces between them. The next two are just as critical. They are always in constant random motion. And third, they attract one another, kind of like tiny magnets. This non-stop movement, that's what scientists call kinetic energy. And here it is, the big link to our food mystery. Temperature is basically just a measurement of how much of this energy the particles have. So when you heat something up, what you're really doing is giving its particles a huge energy boost, making them zip around faster and faster. So what happens when particles from different things start mixing together all on their own? Like the smell particles from your food mingling with the air particles? That whole process has a name. It's called diffusion. And you guessed it, since heat makes particles move faster, it makes diffusion happen way, way faster too. And there we have it, mystery solved. The little particles carrying the smell of that hot food are totally supercharged with kinetic energy. They're just zipping and zooming through the air, spreading out really fast and making a beeline for your nose. But the particles from the cold food, they're kind of sluggish and slow, so they just don't travel very far, which is why you have to get so close. Okay, but what about that third rule, the attraction? There's a really cool analogy for this. It's like watching dancers forming a human chain. See how they hold on to each other? Particles of matter do the same thing. They're held together by these forces of attraction. But here's the catch. Not all these connections have the same strength. Just think about it for a second. A piece of chalk, you can snap that super easily, right? That's because the force holding its particles together is pretty weak. But now try to break an iron nail with your hands. Good luck with that. Its particles are clinging to each other for dear life with an incredibly strong force. And this difference in attraction, it's absolutely fundamental to how matter behaves. So, when you put all these rules together, the spaces, the movement, and the attraction, what do you get? Well, you get the three states of matter that we see all around us every single day. Let's break it down. In a solid, the particles are packed in really tight, just kind of vibrating where they are. That's why solids have a definite shape and a fixed volume. Then you've got liquids. Here, the particles have a bit more energy, so they can slide past one another, which is why a liquid takes the shape of its container. And finally, gases. Their particles have a ton of energy. They're bouncing all over the place at high speeds, completely filling any container you put them in. So the key takeaway here is that every single difference you see between a solid, liquid, and a gas, it all just boils down to two things: how much energy those particles have and how strong the forces are that are holding them together. And what's really cool is that this means we can actually make matter change its state. All we have to do is mess with the energy of its particles. Let's take a look at how that works. And the easiest way to do that, usually it's with heat. When you add heat, you're pumping those particles full of more kinetic energy. You take heat away, you're slowing them down. It's really that simple. This is exactly what's happening when you melt an ice cube or boil a pot of water. Now, that exact temperature where a solid becomes a liquid, that's called its melting point. And for ice, we all know it, it's 0 degrees Celsius, or 273.15 Kelvin if you want to get technical. But something really weird happens right at that specific temperature. Picture this. You have a beaker full of melting ice with a thermometer in it. The temperature climbs up to 0 degrees, and then it just stops. It gets stuck at exactly 0 and stays there until every single last sliver of ice is gone, even though you're still heating it. So what gives? Where is all that heat energy going? This brings us to a really cool idea called latent heat, which basically means hidden heat. That energy isn't making things hotter. Instead, it's being used for a very specific secret mission: to break the bonds that are holding the particles together in that rigid ice crystal structure. It's the energy that's needed just to make the change happen. Okay, so let's wrap this all up. What are the big takeaways? 1. Everything is made of tiny moving particles with spaces in between. 2. Temperature is just how we measure the speed or the kinetic energy of those particles. 3. The states of matter, solid, liquid, gas, are all about the balance between the particles' energy and how strongly they attract each other. And finally, energy doesn't just make things hotter, it's also used to completely change a substance's state. So here's a final thought to leave you with. If everything is just particles in motion, what does that really say about the difference between the solid table in front of you and the invisible air you're breathing? They're made of the same basic stuff. The only difference is how their particles are dancing. Kind of changes how you see the world, doesn't it?
Okay, let's jump right into a question that sounds simple, but I promise it's going to change how you look at everything. The question is the matter all around us actually pure?
I mean, think about it. You go to the store, you grab a carton of milk, and it probably says pure milk right on the label. But is it? Really? Let's put that milk to the test.
And right here, this is where it all gets super interesting. See, for most of us, pure just means there's no weird stuff mixed in, no adulteration. But to a scientist, the definition is way, way stricter. For them, a pure substance is made of only one single type of particle. That's it.
So, going by that scientific rulebook, milk isn't pure at all, not even close. It's actually this really complex, kind of beautiful mixture of water, fat, proteins, and a bunch of other things. And getting that, well, that's the first step to thinking like a chemist.
This idea just blows the doors wide open to the world of mixtures. And as you're about to see, scientists have a really neat way of organizing and unscrambling all the stuff around us.
The truth is, most of the things you see and touch every single day aren't pure substances. The air you're breathing right now, that's a mixture. The dirt outside, a mixture. Even the ocean, you guessed it, a big old mixture. Now, not all mixtures are created equal. They basically fall into two big categories. On one hand, you've got homogeneous mixtures. Think of salt stirred into water. It all looks the same, right? The composition is totally uniform. But on the other hand, you've got heterogeneous mixtures, like oil and water. You can clearly, obviously see the different parts that just refuse to mix.
But wait, there's more. We can zoom in even closer and break things down into 3 really important groups based on what the particles themselves are doing.
So first up, we have solutions. This is your classic homogeneous mixture. The particles that get dissolved, the solute, are unbelievably tiny. We're talking smaller than 1 nanometer. To give you some perspective, a single strand of your hair is about 80,000 nanometers wide. So yeah, these particles are small.
Because they're so tiny, you can't see them, they'll never settle to the bottom, and you can't just filter them out. But here is the #1 thing to remember about solutions. A beam of light will pass straight through them. It doesn't get scattered. Tuck that little fact away. It's going to be important in a minute. Now, let's jump all the way to the other end of the spectrum with the suspension. Think about sand or mud in water.
This is a heterogeneous mixture. The particles are huge, they don't dissolve, and you can easily see them just floating around in there.
And as you'd probably expect, the properties are the exact opposite of a solution. You can see the particles, they absolutely scatter a beam of light, you can filter them out, and here's the big one, it's unstable. If you just leave it alone, all those chunky particles will sink to the bottom.
Okay, so we've got solutions on one side, suspensions on the other. But what about that space in between? Well, that's where things get really cool. That's where we find colloids. They're sneaky because they look perfectly uniform, just like a solution. But if you could zoom way in, you'd see they're actually heterogeneous.
And here we are, right back where we started. Milk. It turns out milk is the textbook example of a colloid. All those little bits of fat and protein are spread out so evenly in the water that it looks smooth, but they're not really truly dissolved. So, this leads to a fantastic question. We know light zips right through a solution, and we know it gets all scattered by a suspension, so what in the world happens when you shine a flashlight through a colloid, like milk? The answer is this amazing phenomenon called the Tyndall effect. The particles in a colloid are in that Goldilocks zone. Not too small, not too big. And that just right size is perfect for scattering light in a way that you can actually see the beam itself cutting through the mixture.
And you've totally seen this before. Check this out. When you see those incredible sunbeams shining through a foggy forest, that is the Tyndall effect in action. The tiny water droplets in the air form a colloid, and they scatter the sunlight, making those beautiful rays visible. It's not magic, it's science. Okay, so if almost everything, from our milk to the air itself, is some kind of mixture, then what does a scientist even consider to be truly pure? Let's talk about the actual fundamental building blocks of matter.
Well, pure substances really only come in two flavors. First, you have elements. These are the basics, the stuff on the periodic table, like iron or gold or oxygen. You just can't break them down into anything simpler. And second, you have compounds. This is when two or more elements get chemically locked together in a very specific ratio, like water, H2O, or salt, NaCl.
And that right there brings us to the final and maybe the most important distinction we need to make. What's the real difference between a mixture and a compound? It's a huge deal in chemistry.
Let me paint you a picture. Imagine you take some iron filings and some yellow sulfur powder, and you just stir them up in a bowl. You have a mixture. The iron is still iron, the sulfur is still sulfur. In fact, you could pull all the iron right back out with a magnet, no problem.
But if you take that exact same mixture and you heat it up, everything changes. A chemical reaction happens. The iron and sulfur atoms literally bond together and they form a brand new substance, iron sulfide. It looks different, it acts different, and that magnet, it has zero effect anymore. You've made something completely new. This chart just lays it all out so clearly. Mixtures are just physically hanging out together. They keep their own properties, you can mix them in any ratio you want, and you can separate them pretty easily. But compounds? That's a chemical marriage. They form a totally new substance with brand new properties, a fixed recipe, and you need another chemical reaction to break them apart. They're a whole different ballgame. All right, so let's do a super quick wrap-up. Remember, scientifically pure means just one type of particle. Most stuff is a mixture, either uniform or chunky. Colloids, like our friend milk, are that special case that scatters light. And the only truly pure things are elements and compounds, which are chemically bonded, not just physically mixed. So I'll leave you with this challenge. Just look around the room you're in right now. At your desk, a glass of water, the window. Now that you know all this, can you start to see the world like a chemist? Can you spot the mixtures, and can you identify the compounds? Give it a try. So what is everything really made of? I mean, everything. It's a question that people have been asking for literally thousands of years. And today, we're going to get into it, diving deep into the building blocks of our entire universe, atoms and molecules. Okay, let's start with a little thought experiment. Grab a piece of paper in your mind. Now cut it in half. Take one of those halves and cut it in half. The question is, could you just keep doing that forever? Or would you eventually hit a point, a tiny little speck, that you just can't cut any further? It seems simple, but this exact question is where our whole story begins. And what's absolutely amazing is that long before any modern science, brilliant thinkers on opposite sides of the world came to the same conclusion. Over in India, around 500 BC, a philosopher named Maharishi Kanad talked about the Parmanu.
the smallest possible particle of matter that was indivisible. And then, a little later in Greece, Democritus and Leucippus proposed the atomos, which is a Greek word that means, yep, you guessed it, uncuttable, or indivisible. For centuries, though, this was just a cool idea, a philosophical concept.
But then, everything started to change. By the 18th century, we're moving out of the realm of pure thought and into the lab. Scientists weren't just thinking anymore. They were experimenting, trying to figure out the actual rules for how matter works. This was the shift from philosophy to hard scientific law.
And one of the first huge rules they figured out was a total game changer. It's called the law of conservation of mass. And the idea is actually beautiful in its simplicity. Mass can't be created and it can't be destroyed. In any chemical reaction, whatever you start with, you have to end with. The total amount just stays the same.
Let me show you what I mean. Imagine you have a sealed flask, and inside you have two different chemical solutions, kept separate. You pop it on a scale and get its weight. Okay, now you tilt the flask. The solutions mix, and a reaction kicks off. Maybe it fizzes, maybe it changes color. It looks like something totally new is being made. But here's the kicker. You weigh it again, and the mass is exactly the same. To the decimal. It proves that matter just rearranges itself. It never actually vanishes.
Okay, so that's rule number 1. Rule number 2 is just as important. It's the law of constant proportions. And what this tells us is that chemical compounds are basically following a fixed recipe. Always. No matter where you find water, for instance, whether it's from your tap or from an iceberg, it's always made of the same stuff in the same fixed ratio. This was a massive clue that something really fundamental was going on.
And you can see it right here. Water is always made of hydrogen and oxygen in a 1:8 ratio by mass. So if you have 9 grams of water, you are guaranteed to have 1 gram of hydrogen and 8 grams of oxygen every single time. Same thing for ammonia. It's always a 14:3 ratio of nitrogen to hydrogen. You see? This consistency, this predictability, it was a giant puzzle piece just waiting to be explained.
So we've got these two amazing laws. Mass is always conserved, and compounds have fixed recipes. But why? Why does matter follow these rules so perfectly? Well, that brings us to the guy who finally connected all the dots.
This is John Dalton. He was a British chemist and teacher who, in 1808, took that ancient idea of the atomos and turned it from a philosophical guess into a real scientific theory that changed everything.
His theory was so elegant. He said, okay, all matter is made of these tiny things called atoms. You can't divide them or destroy them. All atoms of one element, say gold, are identical. But gold atoms are different from, say, oxygen atoms. And here's the crucial part. He said these atoms combine in simple, whole number ratios to form compounds, and boom, suddenly it all made sense. The law of conservation of mass? Well, that's just atoms rearranging. The law of constant proportions? That's because they always combine in the same fixed ratios. It explained everything.
So Dalton's theory was a huge breakthrough. It gave us a whole new way to think about matter. But, it also opened up a ton of new questions. Like, what exactly is an atom? And just how small are we talking here?
The source material has a perfect analogy for this. Think about a giant building. What's it made of? Bricks, right? Each individual brick is the basic unit. Well, atoms are the bricks of the entire universe. From the smallest ant to the largest star, everything is built from these fundamental little blocks.
So how small are these bricks? It's almost impossible to wrap your head around. We measure them in nanometers, and 1 nanometer is 1 billionth of a meter. It's a scale that is just mind-bogglingly tiny.
This chart really helps put it in perspective. Look at the hydrogen atom. Then look at a grain of sand. It's about 1,000,000 times bigger. An apple is another 1,000 times bigger than that. It's just wild to think that the solid world we see around us is made of things that are completely and utterly invisible.
Okay, so we've established that atoms are real and they're incredibly small. But how do we actually describe how they link up to make all the different stuff in the world? Well, for that, we need to learn a little bit of the language of chemistry. And a key word in this language is valency. It sounds complicated, but it's really just the combining power of an element. And I love the analogy for this. Think of it like the number of arms an atom has. Some atoms have 1 arm to link up with another atom. Some have 2, some have 3, and so on. This determines how they can bond together. And we can use this idea to figure out chemical formulas. Let's try it with the crisscross method for magnesium chloride. First, you write down the symbols. Mg for magnesium, which has a 2+ charge, and Cl for chlorine, with a 1- charge. Now for the fun part. You just crisscross those numbers. The 2 from the magnesium slides down and becomes the subscript for chlorine. The 1 from chlorine slides over to become the subscript for magnesium. And that gives you the final formula, MgCl2. See? It's a neat little trick for predicting how these atoms are going to hook up.
So, let's just do a quick recap. We went from this ancient philosophical idea of an uncuttable particle to 2 rock-solid scientific laws about mass and proportions. Then, John Dalton came along with his atomic theory and explained why those laws work. And now we know that everything, absolutely everything, is built from these unbelievably tiny particles called atoms.
But I'll leave you with one final, fascinating thought. Dalton's whole theory rested on the idea that atoms were the end of the line, that they were indivisible. But we now know that's not true. Even atoms are made of still smaller particles, which, of course, leads to the next big question in science. What's inside an atom?
Have you ever wondered what everything is really made of? I mean, the chair you're on, the air you're breathing, it all comes down to these tiny, invisible particles called atoms. And for a long, long time, we thought they were the end of the story. Well, today, we're going to crack that idea wide open. We're going on a scientific detective story to uncover the secrets hidden inside the atom. You see, for centuries, the atom was it, the ultimate building block. Thinkers like John Dalton imagined it as the solid, unbreakable little ball. It was a neat and tidy idea. But science loves to mess with neat and tidy. And this picture, it was about to be completely shattered.
So what if the atom wasn't the end of the line? What if it was just the beginning of a way deeper mystery? Turns out, in the late 1800s, scientists started stumbling onto some really weird clues. Clues that would challenge everything we thought we knew and kick off a scientific revolution. All right, so here's our game plan. We're going to follow the breadcrumbs. We'll see how that old indivisible idea got busted, check out the first attempts to draw a map of the atom, dive into a golden discovery that changed everything, and see how a huge paradox got solved. Then we'll decode what makes elements different and see how we use all this knowledge in the real world. Let's get into it. Okay, first stop. The whole idea of an unbreakable atom starts to fall apart right here with the discovery of something even smaller, subatomic particles. Turns out there were little things hiding inside the atom all along, and finding them forced everybody back to the drawing board. The first clues were, well, they were electric. First, Goldstein found these mysterious canal rays that were positively charged. Then, J.J. Thomson nails down the very first subatomic particle, the negatively charged electron. This was a total game changer. It proved once and for all the atom wasn't indivisible, but it opened up a brand new can of worms. If an atom has positive and negative pieces, how in the world are they all arranged? With these new puzzle pieces on the table, the race was on to build a model, a picture of what the inside of an atom actually looked like. And who better to take the first shot than the guy who found the electron in the first place, J.J. Thomson. So Thomson came up with what we now call the plum pudding model. It's actually a pretty clever idea. He pictured the atom as this ball of positively charged stuff, kind of like a blob of pudding, and scattered all through it were the tiny negative electrons, like plums or raisins. You could even think of it as a watermelon, with the seeds being the electrons. The real beauty of Thomson's model was its balance. You had this big sphere of positive charge, and then just enough negative electrons dotted inside to cancel it all out. The end result? The atom as a whole is electrically neutral, which perfectly matched what scientists were observing. It made a lot of sense. For a while, anyway. Yeah, so Thomson's model was a great first draft, but it was about to be put to the ultimate test. A new experiment was just around the corner. And spoiler alert, it wasn't just going to poke holes in the plum pudding model, it was going to blow it to smithereens. And this is where Ernest Rutherford enters the story. This guy is basically the father of nuclear physics. He set up this famous gold foil experiment really just to test Thomson's model. But what he found? Well, it was far weirder and way more incredible than anyone could have possibly guessed. So Rutherford's setup was pretty simple, really. He decided to shoot these tiny positive particles, he called them alpha particles, at a ridiculously thin sheet of gold foil. Now think about it. If the plum pudding model was right and the positive charge was all spread out, these little alpha bullets should have just zipped right through, maybe getting nudged a tiny bit. But that is not what happened. Not at all.
The results were just shocking. And you don't have to take my word for it. Rutherford himself said, and this is an amazing quote, "It was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you." Can you imagine? It just didn't make any sense. It screamed that something was fundamentally wrong with their picture of the atom. So here's what he actually saw. Most of the particles, the vast majority, did go straight through. That told him the atom must be mostly empty space. But some were deflected. And, this is the crazy part, a tiny few, like 1 in 12,000, bounced almost straight back. The only way that could happen is if they hit something incredibly small, super dense, and positively charged. And boom, just like that, the nucleus was discovered. This was the turning point. Rutherford realized the atom wasn't a pudding at all. It was mostly empty space, with almost all of its mass packed into this tiny, dense, positive center, which he called the nucleus. This was the birth of the nuclear model of the atom. Now, Rutherford's nuclear model was a huge leap forward, but it came with its own giant problem, a fatal flaw, really. According to the physics of the day, the electrons orbiting that nucleus should just spiral into it, causing the whole atom to collapse. So why don't they? Right, this was a massive paradox. The old rules of physics were clear. If you have a negative electron zipping around a positive nucleus, it should constantly be giving off energy. And if it's losing energy, it's losing speed, and it should spiral down into the nucleus in like a fraction of a second. But obviously, atoms are stable. They don't just collapse. So what was going on? The solution came from a scientist named Niels Bohr, and his idea was absolutely radical. He basically said, what if the old rules just don't apply here? He suggested that electrons can only exist in very specific, stable orbits, or shells, and while they're in one of those special shells, they just don't radiate energy. It was a complete break from classical physics, and it not only saved the atom from collapsing, but also kicked off the whole new science of quantum mechanics. With Bohr's rules keeping the electrons in their place, the final major piece of the puzzle clicked in 1932 when James Chadwick discovered the neutron. And there you have it, our complete cast of characters. In the nucleus, you've got the heavyweights, the positive protons and the neutral neutrons. And whipping around the outside in those special shells are the super light negative electrons. The modern picture was finally complete. So now that we have this amazing model, we can finally start to understand what makes all the different elements, well, different. Why is carbon so different from gold? It all comes down to the rules of atomic structure we just figured out. Here's the key. An element's identity comes down to just one number, its atomic number. That's just the number of protons in its nucleus. That's it. If an atom has 6 protons, it's carbon. End of story. 79 protons, it's gold. Now, the mass number is the total of protons and neutrons, and that tells you how heavy the atom is. So protons tell you what an element is, but the electrons, especially the ones in the outermost shell, tell you how it behaves. This is called valency. See, atoms are kind of like people. They just want to be stable. And for an atom, stability means having a full outer shell of electrons. They'll do anything, gain, lose, or share electrons to get there. And that drive is the basis for all of chemistry. But what if atoms of the same element have different numbers of neutrons? Well, these variations are called isotopes, and some of them have some really incredible and incredibly useful properties. Let's check out how we put this knowledge to work. Think of isotopes as different flavors of the same element. Same number of protons, so it's the same element, but a different number of neutrons, which changes its weight and stability. And these subtle differences have huge real-world applications. We're talking about using uranium-235 to fuel nuclear power plants, using cobalt-60 in radiation therapy to fight cancer, and even using iodine-131 to treat thyroid problems. It's amazing stuff. So we've gone from a simple, solid little ball to this complex, kind of bizarre system that's run by the weird rules of quantum mechanics. It's a pretty powerful reminder that what we think we know is always changing. It makes you wonder, right? What are the plum pudding models of our time? What rock-solid truths that we hold today will seem just as quaint tomorrow? What's the next discovery that's going to turn everything we think we know on its head?
Okay, so here's a weird one for you. What do an onion, an elephant, and you all have in common? Now, I know, it sounds like the beginning of a really strange joke, right? But the answer? Well, the answer is actually one of the most profound ideas in all of science.
And that common link is exactly what we're going to dive into today, the fundamental unit of life.
You know, our whole story here starts the way a lot of great scientific discoveries do, with a bit of a chance observation and a brand new piece of tech. We're heading back in time all the way to 1665.
So there was an English scientist, Robert Hooke, and he was looking at this super thin slice of cork, you know, the stuff from tree bark, through a microscope he'd built himself. And what he saw looks kind of like a honeycomb, just full of these tiny empty rooms. And this seemingly small observation, it changed absolutely everything. Hooke decided to call these little boxes cells, which comes from the Latin word for a little room. And just like that, for the very first time, we had a clue that all of life might just be built from these tiny separate units.
Hooke basically kicked the door open, and over the next 200 years, other scientists just rushed right in. First, a guy named Leeuwenhoek discovered entire worlds of tiny, free-living cells just swimming around in pond water. Then you jump to the 1830s, and Schleiden and Schwann proposed that all plants and animals are made of cells. And finally, Virchow adds the last crucial piece of the puzzle. All cells must come from other pre-existing cells. That simple statement was a total game changer, completely shattering the old idea of spontaneous generation.
So all of these incredible discoveries started to build on each other, and they led to one of the most important theories in all of biology.
This is it, the cell theory. It's got three simple but really powerful parts. Number one, all living things are made of cells. 2, the cell is the most basic unit of life. And 3, all new cells come from cells that already exist. This is, quite literally, the foundation for understanding all life on Earth.
And this basic unit, the cell, it can operate in two pretty different ways. Some organisms, like bacteria or an amoeba, they're unicellular. Their entire existence is packed into just a single cell. But then you have others, like us, or plants and animals, that are multicellular. We're made of countless cells that all group together and specialize to do different jobs.
So, if the cell is the basic building block, what's actually inside of it? Let's take a little tour. Honestly, the best way to picture a cell is like a bustling microscopic city.
And pretty much every single one of these cellular cities has three main parts. First, you've got the plasma membrane, which is kind of like the city border, controlling what gets in and what gets out. Then you've got the nucleus. That's the control center, like City Hall. And everything else, the entire landscape inside the city walls, where all the action happens, that's the cytoplasm.
Now that city border, the plasma membrane, is incredibly important. It's what we call selectively permeable, which just means it's a really picky gatekeeper. And one of its most vital jobs is managing something called osmosis, the movement of water. This simple process is how a cell stays hydrated, gets its nutrients, and gets rid of waste. It's a constant balancing act.
And this really shows you how delicate that balancing act is. So, if you put a cell in a solution where there's more water on the outside, scientists call that a hypotonic solution, water just rushes in and the cell swells up. But in a hypertonic solution, with less water outside, the opposite happens. Water rushes out and the poor cell just shrivels up. It's only in a perfectly balanced or isotonic solution that the cell stays stable and healthy.
So, inside the cytoplasm, we find all these little specialized factories and facilities. We call them organelles. The mitochondria, those are the powerhouses generating energy 24/7. The lysosomes are like the waste disposal crew. You've got the endoplasmic reticulum, which is this huge manufacturing and transport network, while the Golgi apparatus acts as the packaging and shipping center. And the vacuoles, well, they're basically the city's storage warehouses.
Now, while a lot of cells share these basic parts, they are definitely not all the same. In fact, by mixing and matching these basic components, nature has created an absolutely incredible diversity in the cellular world.
Okay, so the biggest split is between prokaryotic and eukaryotic cells. Prokaryotic cells, think bacteria, are pretty small and simple. Their nuclear region isn't even wrapped in a membrane. It's just a clump called a nucleoid. But eukaryotic cells, which make up plants, animals, you and me, we're much larger and way more complex. We've got a true nucleus and all those fancy membrane-bound organelles we just toured.
And even within the eukaryotes, there are some pretty big differences. Plant cells, for example, have a rigid outer cell wall for structure, these things called plastids for photosynthesis, and a massive central vacuole to keep up pressure. Animal cells, on the other hand, are a lot more flexible. We don't have a cell wall, and our vacuoles are tiny, if we have them at all.
And here you can see that prokaryotic simplicity up close.
See how the genetic material is all just hanging out in that nucleoid region? Notice the lack of all those complex organelles. It's really life stripped down to its bare essentials. Now contrast that with the incredible specialization of eukaryotic cells. I mean, look at this. From the long branching nerve cell designed to send signals to all the different cells that make up your blood, your bones, and your muscles. These amazing, specialized cells are what make you, you.
All this diversity and complexity, it really brings up one last, really fundamental question. Where do all these different cells even come from? Well, they come from a process we call cell division. This is how organisms grow, it's how we replace old and damaged cells, and it's how life itself gets passed on through reproduction. The two main ways this happens are through mitosis, which is for growth and repair, and meiosis, which is for creating reproductive cells.
And this brings us full circle, right back to our original question, and the most important takeaway of all. What do an onion, an elephant, and you have in common? It's that all of you, all of us, obey this fundamental law. All life, in all of its amazing, beautiful forms, comes from other life, through the division of these tiny, incredible units we call cells.
And that leaves us with one last, really fascinating question to chew on. If a complex organism like you starts from just a single cell, and every single new cell has the exact same DNA blueprint, then how on earth does that organism end up with so many different specialized cells, like nerves, muscles, and bone? That is the next layer of this amazing mystery.
All right, today we're going to get into the incredible biological architecture that allows things to get, well, complex. We're talking about the story of tissues.
So, have you ever wondered how a massive tree gets water all the way up to its highest leaf? Or how a person can run a marathon? I mean, how do these huge organisms even work? The secret isn't about having bigger or stronger cells. Nope, it's something way more elegant. It's all about teamwork.
And that teamwork, that's the core idea here. It's called a division of labor. You see, the real secret to building something huge and sophisticated isn't about a supercell. It's about having a better team.
Just look at this comparison. It really says it all, doesn't it? On one hand, you've got a single-celled organism, like an amoeba. It's a total jack-of-all-trades. It has to move, eat, breathe, get rid of waste, everything, all by itself. But then you look at a multicellular organism like us. It's a whole different ballgame. You have millions of cells that form specialized teams. Muscle cells, their only job is to move. Nerve cells, they just send messages. Blood cells, they transport stuff. They're not masters of everything, they're experts at one single thing.
And that right there is the key. Because each cell has just one job to focus on, it can do that job with just incredible efficiency. This whole idea of specialization, it's the very foundation that makes complex life possible. We're talking everything from the tiniest plant to the biggest whale.
Okay, so what do you call it when all these specialized cells decide to team up and work together? Well, that's when they form something new. They form tissues. So let's put a pin in that. What exactly is a tissue? Well, it's basically a group of cells that are similar in structure, and they're all arranged to work together to get a specific job done. Think about it. Blood is a tissue. Phloem, the stuff that transports food in plants, that's a tissue. Muscle, you guessed it, another perfect example of a tissue.
To really get a feel for this, let's look at two completely different strategies for life, two different designs. We'll start with plants. Their tissues are, they're perfectly engineered for just staying still.
And this chart just lays it all out. Look at the differences. Plants, they're stationary, they're fixed. So what do they need? They need supportive, super rigid tissues. And a lot of the time, those tissues are actually made of dead cells. It's efficient, and it means they use less energy overall. Now, animals, we're a different story. We're active, we're mobile. We need living, flexible tissues and a way higher energy budget to power all that movement. It's these totally different lifestyles that push the evolution of completely different designs for their tissues.
Here's another huge difference you might not think about. Growth. You know, animals tend to grow pretty uniformly, all over. But plants? Nope. They only grow in these very specific, dedicated spots. These are called meristems, and you'll find these little growth factories at the very tips of stems and roots. That's it. That's where all the new growth for the entire plant comes from.
So once these new cells are born in the meristem, they go through this amazing transformation. It's called differentiation. Basically, they get assigned their permanent jobs. They take on a specific shape,
a specific size, and they lose the ability to divide anymore. And just like that, they have matured into the permanent tissues that build the rest of the plant.
Want a great example of this? Let's talk about sclerenchyma. This is a simple, permanent tissue, and its one and only job is to be strong. The cells themselves are actually dead, and their walls are super thick, reinforced with this hard stuff called lignin. That's what makes them so incredibly rigid. You want to know how tough this stuff is? It's the tissue that makes the husk of a coconut nearly impossible to crack.
But not all plant tissues are that simple. Some are complex, meaning they're made of more than one type of cell working together. Take a look at this cross-section of a stem. You see those little clusters? Those are the vascular bundles. You can think of them as the plant's internal plumbing system. They've got two main parts, two tissues called xylem and phloem, and their whole job is to work as a team to transport water and food all over the plant.
Okay, so we've seen the plant playbook. Now, let's switch gears completely and jump over to the animal kingdom. Their tissues are built for a totally different kind of life, one that's all about movement, action, and burning a lot more energy.
And for animals, you can basically sort all their tissues into four main buckets. You've got epithelial tissue, which is all about covering things. There's connective tissue, for support and transport, muscular tissue, which is obviously for movement, and finally, nervous tissue, for communication. So let's just touch on a few of these real quick.
First off, every complex organism, plant or animal, needs some kind of protective outer layer. In plants, that's often a single layer of cells they call the epidermis. It's kind of like a simple biological skin.
Now, animals take that same idea and just run with it. We have epithelial tissue. You can think of it as our living shield. The cells are packed incredibly tight, forming this continuous sheet that acts as a barrier. This stuff makes up our skin, sure, but it also lines all of our organs and blood vessels. It's the barrier that keeps all our different body systems separate and safe.
Okay, let's talk about the engine, muscular tissue. This stuff is all about one thing and one thing only, movement. It's made of these incredible specialized cells that can do something amazing. They can contract and then relax. And that's simple action. When you get millions of them doing it together, well, that's responsible for literally every single move an animal makes.
You know, there's a great question in the source material for this. Blood is a liquid, right? So why in the world would we call it a connective tissue? Well, it's because its job is literally to connect everything in the body. It's the delivery service, transporting oxygen and nutrients to every cell and then hauling the waste away. And unlike those other tissues where cells are packed together, in blood the cells are just kind of floating around loosely in a liquid matrix. And that liquid matrix, we call it plasma.
Okay, so as we start to wrap this up, let's pull the camera back a bit and look at the big picture again. When you really think about it, the entire story of how complex life came to be, it's really the story of specialization.
And that is the big takeaway here. The invention of tissues, that was the absolute game changer. By letting cells team up and specialize, evolution suddenly had the tools to build bigger, more efficient, and way more complex organisms. It's the perfect example of how the whole can be so much greater than the sum of its parts.
You know, this fundamental pattern of specialized parts working together to create something more complex and more capable, that's like the defining rule of biology. It's the blueprint for how life builds complexity. So I'll leave you with a final thought. Where else in the world, completely outside of biology, do you see that same powerful principle at work?
You know, everything in our universe is in constant motion. From the blood flowing in our veins to massive galaxies spinning out in the cosmos. Motion is like the fundamental language that describes everything around us. So how do we speak it? How do we understand it? Well, let's dive in and build our toolkit. Okay, let's start with a question that sounds simple, but is actually pretty tricky. The walls around you right now, are they perfectly still? I mean, your first instinct is to say, yes, of course. But what about the fact that those walls are on a planet that's spinning, and that planet is hurtling through space? The answer, it turns out, really depends on your point of view. And this simple bus ride, it nails the idea perfectly. If you're on the bus, the trees outside are just flying by, but the person sitting next to you seems completely still, right? But for someone on the sidewalk, those trees are stationary, and the bus, and everyone inside it, is what's moving. It's the exact same event, but described in two totally different ways. This tells us something huge. All motion is relative.
So, if everything's relative, how can we ever describe motion accurately? I mean, how do we agree on what's happening? Well, we need a starting point, an anchor to measure everything from. And that is the secret of reference points.
Think about it. If you're giving someone directions, you can't just say, go forward. They'd be like, go forward from where? You have to give them a starting place. That where is absolutely key.
So, that starting point, that's what we call a reference point, or an origin. In this example, the railway station is our fixed point. Without it, saying the school is 2 kilometers north is totally meaningless. It's 2 kilometers north of what? The railway station, the reference point, is what gives that description meaning.
Okay, so once we have a reference point, we can start tracking a journey. But here's the thing, there are two very different ways to measure it. There's the winding path you actually took, and then there's the straight line shortcut from where you started to where you ended up. Let's see why this difference matters so much.
Let's make this super clear. Imagine a car starts right here, at point O, our origin. It drives 60 kilometers down the road to point A. Then it turns around and drives 35 kilometers back, stopping at a new spot, point C.
First up, let's talk about distance. The easiest way to think about this is like the odometer in a car. It just adds up all the ground you've covered, every single kilometer of the trip, no matter which direction you are going.
So, for our car, the total distance is that 60 kilometers out to point A, plus the 35 kilometers it drove back to get to C. That adds up to a total of 95 kilometers. Simple enough, right?
But now we've got displacement, and this is a whole different beast. See, displacement doesn't care about the long, winding path you took. It only cares about one thing. What's the shortest straight-line distance from where you started to where you ended up?
And this is where it gets really interesting. The car started at O and ended up at C. So the straight-line distance between those 2 points is just 25 kilometers. Even though the car's odometer says it traveled 95 kilometers, its final displacement is only 25 kilometers from home.
So here's the crucial takeaway. Think about it. If you run a full lap around a 400-meter track, your distance is 400 meters. But because you end up right back where you started, your displacement is 0.
And this whole idea, this difference between the total path and the start-to-finish measurement, it gets even more important when we start talking about how fast something's moving. This is the difference between speed and the much more precise idea of velocity.
So let's take a look at Usha. She's a swimmer in a 90-meter-long pool. She swims 1 full lap, all the way to the other end and all the way back, and she does it in exactly 1 minute. The total path she covered is 180 meters.
Now, if we want to find our average speed, we just take the total distance, that's 180 meters, and divide it by the time it took, which is 60 seconds. And that gives us an average speed of 3 meters per second. Wow, she's moving pretty fast. But that's not the whole story.
Before we get to the punchline, let's be super clear on the difference here. Speed just tells you how fast you're going. That's it. Velocity is more specific. It tells you how fast and which way. It's based on displacement, not distance.
And here is the mind bender. Because Usha finished her lap right back where she started, her total displacement for the trip is 0. And if her displacement is 0, her average velocity is also 0 meters per second. Think about that. She swam 180 meters at a really high speed, but her overall velocity for the entire trip is 0. Direction changes everything.
So we know how to describe where something is and how fast it's going. But what happens when that velocity itself changes? You know, when you hit the gas in a car or slam on the brakes? Well, that's when we need to start talking about acceleration.
Acceleration is, quite simply, the rate at which an object's velocity changes. And it's not just about speeding up. Slowing down is a kind of acceleration. And even just changing your direction is too, because in all those cases, your velocity is changing.
Okay, let's watch this cyclist. In the first part of his ride, he starts from a complete standstill and speeds up, getting to 6 meters per second over 30 seconds. Then he hits the brakes and his velocity drops down to 4 meters per second over the next 5 seconds. We've got 2 different changes in velocity happening here.
This chart shows us exactly what his acceleration looked like. When he was speeding up, his acceleration was positive. But when he hit the brakes and his velocity decreased, his acceleration was negative. And that's a super important point. Acceleration, just like velocity, has a direction.
Phew! So we have all these concepts: displacement, velocity, acceleration. How in the world can we see the whole story of a journey all at once? Well, the most powerful tool we have for that is a simple graph.
You see, on a distance-time graph, the shape of the line is the story.
If you see a straight, steady incline, that means the object is moving at a constant speed. But if that line starts to curve upwards, it's telling you the object is speeding up. It's covering more and more distance in the same amount of time.
Now, velocity time graphs, they have this really cool hidden secret. The area underneath the line on the graph, it isn't just empty space. It actually represents the total distance the object has traveled. It's an amazing shortcut for understanding the entire journey at a glance.
And all of these ideas we've talked about, reference points, displacement, velocity, and acceleration, they all come together in these three powerful equations of motion. This is it. This is the complete toolkit. With these, if you know just a few things about an object's journey, you can calculate everything else you need to know about it.
And look, these aren't just some abstract formulas you memorize for a test. These are the fundamental rules that govern movement throughout our entire universe. They describe the path of a baseball, the orbit of a planet, the journey of a car down the highway. So the real question is, now that you have the toolkit, what motion will you try to understand?
Force and the laws of motion. You know, it all comes down to one of the most basic questions you could possibly ask about our universe. What makes things move and what makes them stop? I mean, it sounds so simple, right? But believe it or not, this question, it stumped the smartest people on the planet for centuries. And figuring it out, whoa, it wasn't just solving a little puzzle. It literally changed everything we thought we knew.
So let's dive into this puzzle of motion. And to really get to the bottom of it, we've got to start by forgetting what seems totally obvious.
Okay, so for ages, the old belief made a lot of sense. You roll a ball, it slows down, it stops. So its natural state must be just sitting still, right? Seems logical. But then a totally new idea came along from guys like Galileo and Newton. They said, no, wait a minute. An object is perfectly happy to just keep moving. The only reason it stops is because something else is making it stop. Any change in motion has to have a cause.
And that cause? Well, it's got a name we all know. Force. It's just a push, a hit, or a pull. You can't actually see force, but man, you see what it does everywhere. It's the push on a shopping cart, the whack of a hockey stick. It's the simple idea that is the key to this whole thing.
Now here's where it gets cool. Forces can team up or fight against each other. So, picture this. You've got a block and two people are pulling on it from opposite sides. With the exact same strength, what happens? Nothing. The block stays put. That's because the forces are balanced. They just cancel each other out. No change in motion.
But what if one person starts pulling just a little bit harder? Bam! The forces are now unbalanced. And because of that, there's a net force and the block starts to move. So here's the big takeaway. If you want to make something start moving, stop moving, or even just change direction, you absolutely need an unbalanced force. That's the secret ingredient.
And this whole idea, this concept of an unbalanced force being needed for change, it's perfectly summed up in the very first of Isaac Newton's three famous laws of motion.
Here it is, Newton's first law, and it is a game changer. Basically, it says that an object is going to keep doing whatever it's already doing. If it's sitting still, it's going to stay still. If it's moving in a straight line at a steady speed, it's going to keep doing that forever, unless an unbalanced force comes along and messes things up.
And this tendency for an object to resist change in what it's doing, that's called inertia. Honestly, you could just think of it as an object's stubbornness. It really, really wants to just keep on doing its thing.
You've probably seen this. Think about a stack of coins. You take a striker and you sharply hit just the bottom coin. It shoots out, right? But what about the rest of the stack? They don't go flying. Nope. Their inertia, that stubbornness we just talked about, makes them resist moving. They just drop straight down into place. Pretty cool, huh?
Okay, so what gives something more or less of this inertia? It's simple. It's mass. The more mass an object has, the more inertia it has. It's why it's way, way harder to get a train moving from a standstill than it is to push a bicycle. That train just has so much more mass and therefore so much more inertia.
All right, so the first law is all about what happens when there's no unbalanced force. But the second law, well, this is where it gets really good. This law tells us exactly what happens when there is an unbalanced force.
But first, we need a new concept on the table: momentum. You can think of it as the amount of motion an object has. You calculate it by multiplying its mass times its velocity. And this is important because a really fast cricket ball can have a ton of momentum, but so can a really slow-moving truck. And that's why both of them can do some serious damage.
So here's what Newton's second law actually says.
The rate of change of momentum is proportional to the force you apply. Whoa, okay, what does that mean in plain English? It just means that if you want to change something's momentum really, really fast, you're going to need a really, really big force.
And all of that, it boils down to maybe the most famous equation in all of physics. F equals ma. Force equals mass times acceleration. Just 3 letters. But this little formula, it describes how everything moves, from a baseball you throw to a planet zipping around the sun. It's incredible.
Let's bring this back to the real world. Think about a cricket fielder catching a super fast ball. What do they always do? They pull their hands back as they catch it. Why do they do that? Well, that ball has a lot of momentum. By pulling their hands back, they increase the time it takes to bring that momentum down to 0. And because of our F equals ma relationship, increasing the time means you decrease the force. It's a perfect example of physics in action that saves their hands from a lot of pain.
Okay, so we've got inertia down, and we've got F equals ma. Let's get to the third and final piece of this puzzle. And this one reveals something really fundamental about how forces operate in the universe.
I'm sure you've heard this one before. To every action, there's an equal and opposite reaction. That's it. That's Newton's third law. And what it's really saying is that you can't have a force all by itself. They always come in pairs. Always.
So think about it. When a gun fires, it pushes the bullet forward. That's the action. But at the very same time, the bullet is pushing the gun backward with an equal and opposite force. That's the reaction, and we feel it as recoil. Or how about a sailor jumping off a boat? To jump forward, they have to push the boat backward. The boat then pushes them forward. Action, reaction. It's everywhere.
But wait a second. If the force on the bullet and the force on the gun are equal, why does the tiny bullet go flying off while the big gun just kicks back a little? This is where we have to bring back our old friend, F equals ma. The force is the same on both, but because the bullet has way less mass, it's going to have a huge acceleration. The gun has a lot of mass, so it has a tiny acceleration. See? Equal forces, but totally different outcomes.
And that's it. That's the whole shebang. Those 3 simple laws, they're like the source code for motion. They give us a complete framework for understanding why literally everything moves the way it does. So let's recap real quick. Law number 1 is about inertia. Objects just want to keep doing what they're doing. Law number 2 is the math. F equals ma, connecting force, mass, and acceleration. And law number 3 tells us forces are always a two-way street, action and reaction. Which leaves us with one last, kind of mind-bending question to chew on. If every single action force is perfectly canceled out by an equal and opposite reaction force, how does anything ever accelerate? How can a cart even start moving? The answer is hidden in a tiny detail we just talked about. It's a great one to think about. You know, from a simple falling apple to the way entire galaxies dance around each other, there's one single, fundamental force that's running the whole show. And today, we're going to dive deep into that force. Gravitation. So, what could a falling apple possibly have in common with the moon orbiting high above us? It seems like a strange question, right? But this very question absolutely obsessed one of the greatest minds in history. And the answer? Well, it changed everything we thought we knew about the universe.
Okay, so to really get the connection here, we've got to take a step back and think about a basic question. Why do things move in circles in the first place?
I want you to picture this. You're whirling a stone on a string around your head, right? That string is constantly pulling the stone inward toward your hand. It's the only thing stopping that stone from just flying away. If you let go of the string, poof, the stone shoots off in a perfectly straight line. So that constant inward pull, that's the absolute key.
And there's a name for that center-seeking pull. Physicists call it centripetal force. And really, it's like an invisible string that's holding the moon in orbit around the Earth. Seriously, without that force, our moon would have just zoomed off in a straight line into the blackness of space billions of years ago.
So this is where Isaac Newton had his legendary aha moment. He connected the dots. He realized that the force keeping the moon tethered to the Earth was the exact same force that made that apple fall from the tree and hit the ground. Not 2 different forces, but one single, universal force at play. Mind-blowing, right?
And that one single insight, it led to one of the most important scientific laws ever discovered.
Newton basically asked himself, look, if the Earth can pull on an apple, why can't it pull on the moon? Could it be the same force?
His big revolutionary idea was that this pull wasn't special to just the Earth and things near it. No, he figured it was universal, that it acts between any two objects anywhere in the cosmos.
And this became his universal law of gravitation. It sounds complicated, but it's actually pretty simple when you break it down. It really just means two things. One, every single thing that has mass pulls on every other thing that has mass. So yeah, you're actually gravitationally pulling on the screen you're watching this on, and it's pulling back on you. And two, how strong that pull is depends on just two things: how much stuff or mass the objects have and how far apart they are.
Now don't let the math scare you, but this is the whole idea in one beautiful equation. Forget the letters for a second and just look at the bottom part, the d squared. That just means distance squared, and that's huge. It means that as things get farther apart, gravity gets weaker, but it gets weaker fast. If you double the distance, the force isn't just cut in half. No way. It drops all the way down to a quarter of what it was. Gravity's pull fades away really, really quickly.
And the power of this single, simple law was just staggering. All of a sudden, we could explain all these things that seemed totally unrelated, like why we're stuck to the ground, how all the planets do their elegant dance around the sun, and even why the ocean tides come in and out every day. It all came from this one idea.
So that's the big picture. But how does this all play out in our day-to-day lives, right here on Earth? Well, it leads to a pretty weird conclusion. Everything falls at the exact same speed.
Okay, so when an object is falling and the only thing pulling on it is gravity, we're talking no air resistance, nothing else. That's what we call free fall. And when something is in free fall, it doesn't just drop at a steady speed. It accelerates. It picks up speed faster and faster at a very specific constant rate that we just call g.
Now here's where it gets really weird and kind of hard to believe. That acceleration, g, is exactly the same for every object. It doesn't matter how heavy or light it is. You've probably heard the famous story about Galileo dropping two different sized cannonballs from the Leaning Tower of Pisa, right? Well, the whole point was to show that they would hit the ground at the exact same time.
And it's true. If you could get rid of air resistance, say in a vacuum chamber, a feather and a bowling ball dropped at the same time will fall side by side and hit the bottom together. And they both accelerate downward at a rate of about 9.8 meters per second every second. Okay, this whole everything falls the same thing usually brings up a really common point of confusion. So let's clear it up right now. The difference between mass and weight. They are not the same thing.
All right, let's make this super simple. Your mass is the amount of stuff you're made of. It's a measure of your inertia. It's the same number no matter where you are in the universe. Earth, the moon, Jupiter, deep space, doesn't matter. Your weight, though, that's completely different. Your weight is just the force of gravity pulling on your mass. And since gravity changes depending on where you are, your weight changes too.
The perfect example is the moon. The moon is way smaller and has way less mass than Earth, so its gravity is much weaker. So if you went to the moon, you'd weigh only about 1/6 of what you weigh here. You could jump super high. But your mass, the amount of you, would be exactly the same. You haven't changed, just the gravity pulling on you has.
So we've been talking a lot about gravity, which is a type of force. But you know, the effect that any force has can change a lot, depending on how you apply it. This leads us to another really important idea: pressure.
Let's think about this for a second. Why does a sharp knife cut through a tomato so easily, but a dull one just squishes it? You're pushing with the same amount of force from your hand, so what's the difference?
Well, it all comes down to how that force, which we can call thrust, is spread out. The effect of that force completely changes depending on the size of the area you're pushing on. If you concentrate all that force onto a tiny, tiny spot, you create massive pressure.
The formula is dead simple. Pressure is just the thrust, or force, divided by the area. That's why the sharp knife works so well. It takes all the force from your hand and concentrates it onto that razor-thin edge, a super tiny area. The result is an enormous amount of pressure, more than enough to slice right through something.
And once you see this principle, you see it everywhere. It's why a thumbtack has a sharp point. It's why you can walk on snow with snowshoes but sink without them. It's even why you'll sink into soft sand if you're standing on your feet, but you won't sink if you lie down. In each case, you're just spreading the same force, your body weight, over a different sized area.
So that leaves us with one final kind of mind-bending question. If Newton's law is universal, if every object really does pull on every other object, then why don't you feel a gravitational pull from the person sitting next to you, or your coffee cup? The simple answer is you do. The force is really there. But gravity is an incredibly weak force. Because our masses are just so tiny compared to the enormous mass of the entire planet Earth, the pull between everyday objects is so small it's completely unnoticeable. It's a pretty humbling thought, isn't it? Gravity connects everything in the universe, but you only really get to see its awesome power when you start looking at the scale of planets and stars and galaxies.
Today, we're going to talk about two words you probably use all the time: work and energy. But what do they actually mean when a physicist says them? Well, you might be surprised.
All right, let's kick things off with a little thought experiment. Picture this. You are pushing against a solid brick wall. I mean, you're giving it everything you've got. Your muscles are screaming. You're breaking a sweat. But here's the question. Are you actually doing any work?
Well, the answer to that question is probably not what you think. And that's because there's a huge difference between how we talk about work every day and how physics talks about it. You know, in everyday language, we say studying for a test is hard work, or, holding this heavy grocery bag is a lot of work. And yeah, it feels that way. But in physics, the definition is way more specific. It all comes down to one simple, non-negotiable rule. For work to happen, something has to move.
So let's go back to you pushing on that wall. The wall didn't budge, right? So believe it or not, scientifically speaking, you did absolutely zero work on the wall. I know, it feels crazy. You're exhausted, but all that effort, all that energy you used up, it just turned into heat inside your own muscles. It didn't actually do any work on the wall itself.
Okay, so let's nail this down. For work to happen, in the physics sense, you need two things. You absolutely have to have both. One, you need a force, and two, that force has to make the object move. No movement, no work. Simple as that.
Okay, so if we know what work is, how do we actually put a number on it? How do scientists measure it? Let's dive in.
The good news is, the formula is super straightforward. It's just work equals force times the distance it moves. W equals F times S. That's it.
And we measure this in a unit called the joule. So when you calculate work, the answer is in joules. Now, what's a joule? Well, it's not a huge amount of energy. It's roughly the work you do when you lift a small apple, about 3 feet off the ground. So, pretty small.
Okay, now this is where it gets really interesting. Did you know that work can be negative? Yeah. So when the force you're applying is in the same direction as the movement, like when you pull a toy car forward, that's positive work. But what about a force that works against the movement, like friction or a car's brakes? That, my friends, is negative work. It's basically taking energy out of the system.
So all this talk about doing work, it leads us right to another huge concept: energy. You really can't talk about one without the other. They're like two sides of the same coin.
So what is energy? The simplest way to think about it is this. Energy is the ability to do work. That's it. If something has energy, it means it has the potential, the capacity to make something else move.
And this connection is so fundamental, so direct, that guess what? They're measured in the exact same unit. That's right, energy is also measured in joules. It's a perfect little clue that tells you just how linked these two ideas are.
And energy isn't just one thing, right? It's all around us in all these different forms. You've got the chemical energy in your lunch, the electrical energy lighting up your room, the light energy coming from the sun. It's literally everywhere.
For now, though, let's zoom in on one specific type, mechanical energy. And this one is super cool because it breaks down into two main types that are all about motion and position.
On one hand, you've got kinetic energy. That's the energy of motion, the energy something has because it's moving. On the other hand, you have potential energy. That's stored energy, energy that's just waiting to be used. I love the idea of it being the energy of doing versus the energy of waiting.
So anything that's moving has kinetic energy. A car driving down the road, water flowing in a river, you name it. And here's the kicker. The formula for it has velocity squared. What does that mean? It means if you double an object's speed, you don't just double its energy, you quadruple it. Speed is a huge factor here.
Potential energy, on the other hand, is all about that stored-up readiness. You stretch a rubber band, you've just loaded it with potential energy. You lift a bowling ball off the ground, you've given it gravitational potential energy. It's like a coiled spring, just waiting for the chance to do something. And this is where you see the beautiful dance between them. Think about an archer. When they pull back that bowstring, they're packing it full of potential energy. The second they let go, whoosh,
All that stored potential energy instantly transforms into kinetic energy, sending the arrow flying.
This idea of energy changing forms, from potential to kinetic and back again, it brings us to one of the biggest, most important rules in all of physics. I mean, this is the big one.
It's called the law of conservation of energy, and it basically says this. You can't create energy, and you can't destroy it. All you can do is change it from one form to another. The total amount of energy in the entire universe has been the same since the beginning of time and will be the same forever. It just swaps outfits.
Let's go back to that falling object. When it's held up high before you drop it, it's packed with potential energy, but has zero kinetic energy. As it falls, it's losing height, so its potential energy goes down, but it's gaining speed, so its kinetic energy goes up. And right before it hits the ground, it's all kinetic, almost no potential. But here's the magic part. If you add the potential and kinetic energy together at any point during its fall, the total is always the same. It's just a trade-off.
And that powerful law leaves us with a huge, mind-bending question to chew on. If energy can never be created or destroyed, and it's just been changing forms this whole time, then where did all of it come from to begin with?
You know, we're surrounded by sound all the time, but have you ever stopped to think about what it actually is? It's way more than just, well, noise. So today, we're going to trace the incredible unseen journey of sound, starting from a tiny vibration all the way to a tool so powerful it can literally see inside us.
Okay, so what is sound, really? Well, at its core, it's just a type of energy. It's not something you can grab or see like light. Think of it as this special kind of wave that travels to our ears, and then our brain does the amazing job of translating that wave into everything we hear.
And here's the absolute #1 rule, the starting point for every single sound you've ever heard. For a sound to exist, something has to vibrate first. That's it. No vibration, no sound. It really is that simple.
All right, so let's dive in at the very beginning. How is sound even born? What's the source of everything we hear?
You know, when we say vibration, we're talking about a super fast back and forth movement. Just think about it. A guitar string when you pluck it, a tuning fork after you strike it, even your own vocal cords, they're all creating sound by doing that exact same thing, moving back and forth really, really fast. That little dance is the birth of sound.
Okay, so a vibration happens and poof, a sound is born. But that's only half the story, right? How does that sound get from the source all the way to our ears?
Well, here's the thing. Sound needs a ride. It can't just travel through empty space. That's why in space, no one can hear you scream, right? It needs some kind of stuff to move through, and we call that stuff a medium. And that medium can be just about anything, the air, water, or even a solid object like a table.
Now, what's really fascinating is how it moves. Imagine you've set up a long line of dominoes. When you push the first one, that wave of falling dominoes zips all the way to the end. But each domino itself doesn't actually travel down the line, right? It just falls into the next one. Sound is exactly like that. The particles in the air don't fly from a speaker to your ear. Nope, they just bump into their neighbors, passing the energy along as a wave.
And because those particles are vibrating back and forth in the same direction that the wave is moving, like a push forward, we call sound a longitudinal wave. It's basically a series of pushes and pulls traveling in a straight line.
The best way to picture this? A slinky. If you push one end, you see this wave travel down it, right? You get these parts where the coils are all bunched up. We call those compressions. And then you get these parts where they're all spread out. Those are rarefactions. That pattern of bunching and spreading is precisely how a sound wave moves.
Okay, so we know how sound is born and how it travels, but what makes one sound different from another? You know, its unique identity?
I mean, a high-pitched whistle is totally different from a deep bass drum, right? Well, those differences really just come down to two main things, frequency and amplitude. Frequency is basically how fast the wave is vibrating, and that's what gives us pitch. And amplitude is how big the wave is, which we hear as loudness.
It's pretty straightforward. The faster something vibrates, the higher the frequency of the sound wave. And our brain hears that high frequency as a high pitch. So, a tiny bird chirping is creating way more vibrations per second than a big rumbling truck.
Loudness, on the other hand, is all about raw power. The more energy or force you use to create that vibration, like whacking a drum hard versus just tapping it lightly,
the bigger the amplitude of the wave. And a bigger amplitude means a louder sound. A whisper is a tiny little wave, while a rock concert is well, a giant one.
But sound doesn't just travel in one direction and disappear. It actually interacts with its environment. It can bounce off stuff, which leads to some pretty cool effects.
Just like a rubber ball bounces off a wall, sound waves reflect off surfaces too. And this reflection is exactly what creates an echo. You shout in a big, empty space, the sound wave hits a distant wall, and boom, it bounces right back to you.
But wait, why don't you hear an echo in your bedroom? Well, here's a cool little tidbit about our brains. The sensation of any sound we hear lingers for about 1/10 of a second. So, for our brain to even notice the reflected sound as a separate thing, an echo, the sound has to travel to the wall and back in more than that 1/10 of a second. And for that to happen, the wall needs to be at least 17.2 meters away. Any closer, and the two sounds just blend together.
And what's really cool is that we figured out how to use this to our advantage. Things like megaphones, or even the specially curved ceilings in concert halls. They're all designed to reflect sound in a very specific, controlled way, to aim it right where it needs to go.
But here's where things get really wild. The story of sound doesn't stop with what our ears can pick up. There's a whole invisible spectrum of sound out there that we can't hear at all.
You see, the range of human hearing is pretty limited, from about 20 hertz on the low end to 20,000 hertz on the high end. Sounds below our range are called infrasound. Think of the deep rumbles that elephants use to communicate. And sounds above our range, that's ultrasound. It's what bats and dolphins use to see in the dark.
And this is where it really feels like science fiction. We've actually learned how to use that ultrasound, sound we can't even hear, for some incredible things. We use it to clean tiny, delicate parts, to find invisible cracks in metal, and maybe most amazingly, to create images of our own organs inside our bodies. Just think about that. We're using sound we can't even hear to see inside solid metal and our own bodies. It really makes you wonder, what are we going to uncover next with these invisible waves? It all just goes to show that something that starts as a simple, tiny vibration can turn into a tool that completely changes how we see the world. It's a pretty powerful reminder that there's so much happening right outside the limits of our senses.
So how in the world are we going to feed billions of people on a planet that isn't getting any bigger? It's one of the most critical questions of our time. Today, we're going to break down the science behind how we can improve our food supply. Let's dive right in. Let's start with a number, just to wrap our heads around the sheer scale of this. 250 million tons. That's 250 million tons. That's how much grain a single country, India, is going to need every single year. And you guessed it, that number is only going up. And right there, that's the real kicker. We need all this extra food, but we can't just, make more land. Places like India are pretty much already using all the farmland they've got. So we can't build outwards. The only way to go is up. We have to get more food from the land we already have. But this isn't just a simple math problem where you just grow more stuff. The challenge is actually way more complex than that. And that brings us to this really important idea: food security. See, food security isn't just about having food available. You could have giant warehouses overflowing with grain, but that means nothing if people can't actually get to it or afford it. Real food security means that every single person has access to the food they need, both physically and economically. That's a huge distinction to keep in mind as we go through this. So how do we pull this off? How do we increase our yields without wrecking the planet? Well, scientists have a pretty clear 3-part game plan to tackle this whole thing head-on. It really boils down to 3 big steps. First, you make the seeds themselves better. Second, you get smarter about how you grow them. And third, you have to protect the crops from all the things that want to destroy them. And as you'll see, these aren't just 3 separate ideas. They all work together in this really powerful, interconnected system. All right, let's jump into stage 1, improving the actual seeds. This is all about tinkering with the genetic foundation of our food. One of the most powerful tools in the toolbox here is something called hybridization. Honestly, think of it like being a matchmaker for plants. Scientists take 2 different parent plants and cross them, hoping to create a new version, an offspring that has the absolute best qualities of both parents. This is how we literally design crops to be better. So what are they actually breeding for? Well, a higher yield is the obvious one, right? Just getting more food. But it's so much more than that. They're also aiming for better quality, like wheat that bakes better bread. They want crops that can fight off diseases, pests, and even handle stressful things like a drought. And here's a big one, a shorter growing season. If a crop matures faster, farmers can potentially get 2 or 3 harvests in a single year, instead of just one. Game changer. Okay, so you've got your new and improved super seed. That's stage 1, check. Now for stage 2. How do you actually take care of that crop out in the field? This is all about smarter farming. A plant needs food to grow, and it gets that food from the soil. Now, you can give it that food in 2 main ways. You've got manure, which is organic. It's great for the soil structure and helps it hold water. Then you have fertilizers, which are made in a factory and give the plant a super concentrated dose of specific nutrients. Now, fertilizers can give you a quick boost in yield for sure, but using too much for too long can actually hurt the soil. The real key is finding that perfect, sustainable balance. Beyond just feeding the plants, the way you plant them is a huge deal. One cool technique is called mixed cropping. It's kind of like diversifying your stock portfolio, but for your farm. By planting, say, wheat and chickpeas together, if some disease comes along and wipes out the wheat, you don't lose everything. You still have the chickpeas. It's a really simple insurance policy against total disaster. Now, a more organized version of this is intercropping. Here, you aren't just randomly mixing seeds. You're planting different crops in a very specific pattern, like 1 row of this, 1 row of that. The crops are picked because they actually help each other out, using different nutrients. Plus, that pattern can make it way harder for pests to spread and wipe out the whole field. And here you can see exactly what that looks like. You've got these clean, alternating rows of different plants. It's not just pretty. This organized system makes sure that all the resources, the sunlight, the water, the nutrients in the soil, are being used as efficiently as humanly possible. And finally, there's crop rotation. This one is all about playing the long game, thinking across different seasons. Instead of planting the same thing in the same field year after year after year, you have a planned out sequence of different crops. This does amazing things, like naturally putting nutrients back into the soil and, crucially, breaking the life cycles of pests and diseases that might be hanging around. So, you've picked a great seed, you've nurtured it with all these smart farming practices, but you're not out of the woods yet. The job isn't done. Now we have to tackle the third and final stage, protecting your harvest. Because out in the field, the threats are just relentless. You've got weeds, which are basically just bullies stealing food, water, and sunlight from your crop. Then you've got an army of insect pests that attack the plant from every angle, chewing the roots, sucking the sap, you name it. And on top of that, you have diseases caused by things you can't even see, like bacteria and fungi. Any one of these can absolutely ruin a harvest. So what do? Well, yeah, chemical pesticides are one tool, but there's a huge push now towards prevention. And this is where it all comes full circle, right? Remember those pest-resistant seeds from stage 1? Or using crop rotation from stage 2 to break pest cycles. It's all connected. The best defense is a good offense. So we have our 3 stages: better seeds, smarter farming, and better protection. But here's the real takeaway. The secret sauce isn't in any one of these steps. The magic happens when they all work together as one big integrated system. This is how you build a successful, sustainable farm. It all has to work in harmony. You start with those high-quality, tough-as-nails seeds. You give them exactly the water and nutrients they need. No more, no less. And you protect them with a smart, integrated approach that doesn't just rely on chemicals. Each part of the system makes the other parts stronger. Which brings us all the way back to the beginning. We've just walked through the incredible science that lets us grow more food than ever before in human history. But I want to leave you with this question. Is just producing more food actually enough to solve world hunger? Or is that challenge of access, making sure people can actually get the food, just as important as the challenge of production? It's definitely something to think about. Thanks for joining me for this explainer.